objective summary. So, we conducted an inspection, testing, and performance evaluation of the local exhaust ventilation, also known as LEV system, which are located at the Mitsubishi Chemical Sdn Bhd in Terengganu. Our purpose is to ensure compliance with use regulations 2000 and factories and machinery regulations 1970. The LEV system is one fume hood installed in the polypropylene laboratory. The measurements also included are the phase velocity, the duct transport velocity, and the fan performance. Based on our findings, we found that all tested parameters met the ACGIH recommended values, and the phase velocity was on the lower end of the acceptable range, which is 83 fpm. Also, the overall system condition was good, with no leakage and no cross-draft detected, and our recommendation would be to include minor improvements to system performance and user practices suggested. So, for the introduction of our report, the testing date were in 22 April 2025, and our objective are to assess effectiveness of LEV system in labs and also to monitor for compliance with occupational health regulations. So, our process overview are that the chemicals retrieved from store are used on experiment tables or inside fume hood, and the fume hood controls exposure to hazardous vapors. The LEV system details are that one system are inspected, which is the fume hood, and the system ID are LEV-fume-hood. Also, it is installed in the polypropylene laboratory, and the duct type are a PVC ducting type, and its fan are centrifugal type.
For our methodology, we conduct a comprehensive inspection and performance evaluation of the local exhaust ventilation or LEV system at the polypropylene laboratory. First, we use several key instruments: an anemometer for phase velocity, a pitot tube and manometer for pressure readings, a tachometer for fan speed, and a smoke tube for visual airflow check. We began with a visual inspection of the LEV system, checking for corrosion, leakage, or physical damage. We also evaluate the positioning of the hood and ensure that the sash opening and workspace were clear and properly labeled. Next, we carry out three main measurements. First, velocity was measured using the crate point technique to determine how effectively the hood captures contaminant. 2. Static and velocity pressure were measured using the pitot tube and manometer to calculate transport velocity and total pressure drop. 3. Fan speed was measured with a tachometer, and from that, we calculate key performance metrics like fan static pressure, total pressure, brake horsepower, and airflow rate.
We first inspected the fume hood system visually. The hood, ducting, and fan were all in a good condition, which is no leaks or corrosion. The smoke test passed, showing no cross draft, which indicates proper contaminant. Some chemical bottles and tools were placed inside the stage, but they didn't block airflow. This schematic diagram of the system is illustrated in figure 4. This provides a clear overview of the airflow and component layout. This laboratory is equipped with only one fume hood, which is used to control and extract hazardous contaminants such as gases, vapors, and smoke. The fume hood plays a vital role in ensuring the safety of laboratory personnel by preventing exposure to harmful substances. A visual representation of the installed fume hood is shown in figure 5. During this assessment, the phase velocity of the fume hood was tested to evaluate its effectiveness in capturing and removing airborne contaminants. This parameter is crucial as it determines whether the hood can provide adequate protection to the laboratory users. The result for the phase velocity was recorded at 83 fpm within the recommended 80 to 100 fpm range. This means the hood can put in air effectively, although it's near the lower limit, so periodic checks are needed. The calculated flow rate was 753.83 cfm, close to the baseline. Next, we check the hood transport velocity. This is to determine whether the airflow within the ducting system meets the required performance standard for effective contaminant transport. To measure, we are using a manometer and pitot tube and took measurement at 4 points in the duct. The result velocities ranged from 1,699 to 1,835 fpm, all within the recommended 1,000 to 2,000 fpm range. This shows the system can carry contaminant effectively throughout the duct. Next is the fan measurement. This is to determine key parameters such as revolutions per minute, fan static pressure, total pressure, brake horsepower, and airflow rate. These measurements are essential to verify whether the fan system operates effectively and meets the required ventilation standard. The result for fan speed was 2,790 RPM, that very close to the baseline of 2,800. Static and total pressure were also nearly the same at the baseline, and the airflow was 625 cfm, just slightly lower than expected, so fan is functioning effectively. To summarize, phase velocity is safe but close to the minimum, so regular checks are recommended. For transport velocity, is within the safe limit, and the fan system is stable with consistent RPM and pressure. Visually, there were no system issues. However, minor concerns were observed with user practice. Based on our observation, we found out that the apparatus and chemical bottle are placed near to the such opening. This might be potential to disturb the airflow and reduce dirt infection. The best work practice for workers can apply is: the first one, keep the apparatus 6 inches inside the fume hole. Second, avoid overloading at such area. And the last one is conduct regular inspection and training for lab personnel.
Next, recommendation. Recommendation in system improvement. First, the system improvement must be taken is increasing the phase velocity toward optimal range and hence protective efficiency. The phase velocity should be adjusted slightly upward for ensuring better containment, especially in variable room conditions. Second, the regular flow balancing and inspection of fan static pressure are needed to prevent energy loss or dust buildup, like improving duct transport velocity and pressure loss minimization. Third, install real-time monitoring indicators, which is adding airflow indicators or low flow alarm on the fume hood helps laboratory user instantly detect ventilation failures. Next, recommendation in work practice improvement. First, ensure clear such opening during operation, which is strictly SOP should be enforced to keep chemical bottles and apparatus away from such openings to reduce turbulence and maintain optimal airflow patterns, even though current obstruction do not block airflow. Second, implement comprehensive LEV user training, like staff should be trained in proper such head usage, positioning, work well inside the hood, and avoiding sudden body movement that disrupt airflow. Third, introduce LEV usage SOP and lab signage, which is clear signage on proper hoods use, do's and don'ts, and emergency protocols should be installed to standardize work practice and increase awareness among lab users. Lastly, recommendation in regulations compliance and others. First, adhere to Regulation 17 and 18 of USH 2000, which is ensuring monthly internal LEV inspection and annual performance testing by a competent hygiene technician. Second, maintain full record keeping, like document and archive design specifications, test report, inspection log, and maintenance schedule in line with Regulation 19 and DOSH record keeping guidelines. Third, prepare for power failure contingencies, which is a contingency plan should be developed to respond to LEV breakdowns or power failures to prevent uncontrolled chemical exposure in emergencies.
On our finding, LEV system in the mechanical engineering laboratory is functioning and compliant, but operating near the minimum acceptable performance level. Our phase velocity result range from 100 to 109 feet per minute, which meets the minimum standard but could be improved for more efficient contaminant capture. The calculated fan performance values: fan static pressure of 3.17, total pressure of 3585, and brake horsepower of 2.08 show that the fan is working adequately. No sign of damage or leakage were found during inspection, and the airflow pathway were clear, indicate good structural condition. In terms of our objective, the system is effectively minimizing exposure to contaminants. All required measurements were taken and matched closely with design expectation. No damage or malfunction was detected. And importantly, the system complies with DOSH and USH regulation. Overall, we recommend minor adjustments such as optimizing fan speed and improving user practice to enhance the overall safety and performance of the ventilation system.